Okay, so now in the last section for today, I think we've achieved something. I actually now clarified what I want to do, and so what I want to show you is how to do maximum likelihood estimation for something that you are very familiar with, namely the GLM, and specifically simple linear regression. And we will do two approaches: one, the analytical approach that you are familiar with, and then I will use this also as an example to show you how to use fmin search and using function handles. Yeah. So essentially, this example now should tie a lot of things together that we have seen over these programming courses and also some stuff from the statistical methods part. So and this whole thing will be done writing a example script. So let's call that simple linear regression. Simple linear regression estimation. It's quite long. Anyway, SLR. Let's call it SLR. Simple linear regression estimation. This tutorial script introduces analytical and numerical estimation. Introduces the numerical estimation of the effect size parameter. And what are the parameters in simple linear regressions? In simple linear regression, the beta parameters. What do they refer to? Yeah, so the offset and the slope. So these are the parameters, the effect size parameter, offset and slope of a simple linear regression GLM. So this is what we want to do now, which also might help you with the GLM stuff. And I'm writing it, as you see now. Good. So then let's follow the general idea of probabilistic models, so that you formulate a model, then you get some data, and then you estimate the model. And this we will do now in code form. And I wanted to say something. And yeah, let's just do it. So the first thing is that we want to do some model formulation. So we need to decide on how many data points we are interested in. And I'm defining that we are interested in 10 data points. And then we need some values, because we're doing simple linear regression. We need some values for our independent variable. So let's use here. Let's just make it simple. We use the values 1 to 10. And then we need to define, of course, if we want to define the model of a GLM, we need to define the design matrix for simple linear regression. So how does the design matrix for simple linear regression look like? No idea, or you don't want to say it? Or?
What are the elements of the design?
Hmm?
What are the elements of the design matrix?
No, yeah, that's the question. For specifically for simple linear regression. You know that the general GLM, of course, has this form. And how does the design matrix look again for simple linear regression? Okay, no, it doesn't look like the identity matrix. It has a column of ones for the offset, and then the values of the independent variable. Yeah? So it looks as follows. We need to concatenate a column of ones with n rows, which are the number of data points, and our values of the independent variable. Actually, we need to transpose that, because this here will generate a row vector, and we want it as a column vector here. So we here define the design matrix.
What is the apostrophe for?
Yeah, that's the transposition. If you think we did that when we talked about vectors, if you have something like this, you get a row vector, and if you put the apostrophe, it's transposed, so you get a column vector. So let's look at the design matrix. Something is not working. Sorry. Once n rows and one column, and not one column and rows. So this is the design matrix. Please, from now on, remember that for simple linear regression. I ask you that every 2 weeks. In case you didn't realize, I always ask you again what the simple linear regression design matrix is. It has a column of ones, and it has the values of the independent variable as another column. Yeah, so that's the thing that I wrote up manually many times in the other course. Before we do more, let's put this here. So now we have essentially already formulated the model. How from this specification, if you would like to specify the number of parameters, what is one way to do that? So from the design matrix, how many parameters do you have? Beta parameters? Because we of course have also the sigma parameter, but talk about beta parameters. 2. And how do I get this from what I've specified so far in this code? So how do I get the 2 columns? For example, I can use size x and basically ask MATLAB for the number of columns, so that's the second dimension of x, and then I get p, because I could also define it. Doesn't really matter. Now I read it out from the design matrix. But now I think I have everything in terms of the model, in terms of the structural part. So this X is now defined. Now, of course, if you want to sample data, you need to specify true but unknown parameters. So let's say for, so I'm calling this better true but unknown now. Better true but unknown. Let's say we have typical example offset 2 and slope. Let's not take 1 but take 0.5 to make it more interesting. So the first one is the true but unknown slope, which is 2, and the second one is the true but unknown. The first is the true but unknown offset, and the second one is the true but unknown slope, because they get multiplied with these parts of the design matrix. Of course, we need to specify another parameter, which is what? We want to specify the GLM, what is next to the beta parameter, what is the other parameter? Yeah, but it's about by epsilon, but the
Error?
yeah, and how is that called? At least in my world, but also in the general world. Well, that's our sigma square. Yeah. Let's see. So we will visualize it, and then we will set it to 1 now, but we might change that. So that's the true but unknown variance parameter. Also specified that. And now we have everything to actually obtain a realization. So this is now of course the thing where in real life you cannot do this. This is a simulation, and in real life you would now do the experiment and obtain some data, but we will simulate some data. And this can be done with the multivariate normal random number generator in MATLAB. So this generates random numbers from the multivariate normal distribution with expectation parameter mu and variance parameter sigma. So what is our mu? X beta, exactly. So we can compute that if we want. Can either do it like this, so we can compute this matrix product and then pass it into the function, or we can directly pass it into the basically compute it on the fly. So we compute our mu, so our expectation beta, our expectation vector here. Let's compute it previously, then it's easier to visualize that. So let's do it here. So that's now our true but unknown expectation parameter. And then, of course, to get a sample from a multivariate normal distribution, we also need to specify the design matrix. Maybe we also do that here outside. So sigma is specified. We want to sample independently. So what is our big sigma here? What's the covariance matrix parameter of the multivariate normal? For the GLM, if you have independent samples. Maybe I write something up here, and you might remember. So what's our covariance parameter? I ask you that every week. Anyway, so it's the sigma square, the variance parameter times the identity matrix. Yeah. This is not news to you, or it shouldn't be. What's going on? No one knows. Okay. Covariance parameter. So, and then we put that in. And sample data. So, and then we do some visualization of the whole thing, because we can. So, here we had model formulation, and I would conceive specifying the true but unknown parameters as part of model formulation. This is now model realization. This is not something that, of course, you do in real life, only in simulations. And now let's visualize this. So let's plot our x and our mu, maybe black. Oops. And plot our data realization in blue. Well, that depends. We can also just call it expectation, call it our data. That looks maybe without this. So now you see what I always talk about in statistical methods. We've seen that before. So I drew it by hand the other day, and here we now did it automatically. So here we have the value of the independent variable x, and we have then computed the expectation of this multivariate normal, which you see here with the true but unknown parameters 1. True but unknown parameters 2 and 0.5. So here you get 2, and then you have plus 0.5, so you get 0.5, and you see that the slope is it's 0.5. So let's see for an example. So if you go from 2 to 3 on the x-axis, you go up 0.5 on the y-axis, so the slope is 0.5. Let's make this a little bigger. So, same thing, that doesn't look that nice. But as you can see, there's quite some noise. So this is of course a function of our sigma parameter. So for example, if we make this smaller by an order of magnitude, so if we specify this to be 0.1, then you will see that the data points, the sample data points, are much closer to true but unknown expectation. If we make it even smaller, you see that they're almost identical, so maybe let's leave it at that. And now we assume that we don't know our true but unknown parameters, but we want to estimate them, and we only want to estimate actually our beta parameters. So there are two ways that we want to do that. First, analytical estimation of beta parameters. So you know how to do that. So what's that? What's our maximum likelihood estimate for beta? Come on! So what's the formula to compute the beta parameter estimate? Guess. You're really not working on this, huh? So you're working on writing blog posts and stuff, but not working on doing science.
Is that the X transpose?
Exactly. Yeah, can you say it again? So
X transpose X inverse
Mhm.
X transpose
yeah. So it needs to be inverted. So in MATLAB, if you watch my following the sleep video, to compute the inverse of a matrix, you can use this inf command. There are other ways to do it, but this is, in my opinion, the easiest to see. So what this means, this inf is this to the power of minus 1. So the MATLAB expression for that is inf. So invert this and multiply with the transpose of x times y. Well, that's just application of ML estimator. And then that's actually a nice feature of MATLAB. Or not a nice, like many things are not nice. It actually doesn't return y as a column vector, but as a row vector for some reason. If one transposes the outcome of this, then one actually gets y as a column vector, which would make sense anyway, because it's the outcome of a multivariate Gaussian is always a column vector. And then this formula works. And then we can also plot our predicted data. So maybe let's evaluate that here. Maybe let's call this beta head A for analytical, because we will do the numerical in a second. Evaluate predicted data. So that's y predicted based on the analytical version. So we take our design matrix and multiply that with our analytical estimate. And then we also plot that. And we can call this analytical fit. So I have a hard time seeing this. Let's make it's easier to see. Maybe let's put the so now what you see here is what I'm always talking about in statistical methods. So you see the true but unknown parameter in black, and then you see the data points, and then you see the fit to the data points, which of course deviates a little bit from the true but unknown stuff. So the typical way that you've seen this previously, maybe if I increase the noise again a little bit, so the variance parameter is of course without the true but unknown parameter. So you're familiar to seeing this. No, I did something wrong, did I? Oops. So this is how you're familiar with seeing this. So you have some data points and you have a straight line fit in there. So this is what you've seen many times. Now, because we have done it model-based and we've done a data simulation, we can also plot the true but unknown value, and you can see that this can, if the noise is large, it can deviate quite a lot, as you see here. Let's make the noise smaller again, maybe 0.5, so that maybe a little bit larger. I have time. Nothing else to do today than teach. So here you see that there's some deviation between the fit and the true but unknown data. So that was all preliminary stuff to now introduce the numerical estimation. Yeah, but I hope it also helps you a little bit with understanding the GLM. Now we want to do, based on the data, we want to do a numerical estimation, which of course in this case we don't have to do because we have a formula to get the better estimates. But often in real life, when you have more complex models than the GLM, you don't have a formula to get the parameter estimates. So you use numerical computing to do that. And this will now basically use the idea of the applying F-min search to the log likelihood function. So of course, what we need to do first is, if we want to now numerically maximize the likelihood function or the log likelihood function, we need to write a MATLAB function that actually implements the log likelihood function. Yeah? And this is what we are going to do next. I'm starting to have fun. You look a little bit like you're not starting to have fun, but now this is something that's more real than this. Here you have a data array, you extract one element. Yeah, that's horrible boring. And now we're doing here a probabilistic model estimation numerically, empowering you to do science. Yeah, it's the good stuff now. So we now want to write down or write a function that returns the log likelihood. So, and this also should make clearer a little bit actually the log likelihood stuff that we talked about. So we define a function here that we call log likelihood, and we give it, sorry, what am I doing? So, well, we can call it, let's call it L, and let's call the function log likelihood. Maybe let's call it more specifically, it's the simple linear regression log likelihood. Yeah? So that's more specific what's going on. The output is LLH, so that's a number, and as inputs, and there you have to be a little bit flexible in your thinking. So you know that the likelihood function is a function of the parameter, but also depends on the data. Yeah. So to implement this, one way to implement this, of course, there are different ways, is to actually pass both data and parameter as an input to the function. So let's do that. So we put in beta and y, and now we write our help. And this function evaluates the log likelihood of data y for parameter value beta for the case of a simple linear regression. We actually do it differently. Simple linear regression GLM. I'm actually doing it differently. I'm using the structure approach that I'm so fond of. So we actually put in LLH. The input is LLH, which is a structure. And as we've seen this morning, structures have fields, and these fields are y. That's the n times 1 data. Beta, which is our 2 times 1 beta parameter vector. Then we need, if we evaluate the likelihood, you know that this also depends on the variance parameter. So this is our scalar known variance parameter. So we, because I don't want to estimate both parameters, so I'm assuming that we know the variance. Like I said earlier in the statistical methods, it's more a teaching assumption that's not happening in the real world. So that's our scalar known variance parameter. And to compute the likelihood, you also know that we need to have the design matrix. N times 2 design matrix. Outputs. Our output is also LLH. Which is of course the input structure, but with additional field LLH, which is the log likelihood of y for data of data for parameter. So now I've specified what I said one should specify first, so some help. Now we need to actually do that. So to get started, we might here return log y, just to do something. So the first thing with this, the first thing is that we need to specify the input structure. So we are defining this structure now. So we had y, for which we set y beta of y for beta 0, 0. So if we assume that the beta parameters are 0, 0, what is the log likelihood of the observed data? And that's what we're doing here. I'm just doing this right now not to estimate things, but to get this log likelihood function to work and show you what's going on. And our sigma square we also need. So, and then we call we're now calling our simple linear regression log likelihood function with this input structure, by this, when we do this, get here. So we have now our input, and now can compute the log likelihood. So what's the log likelihood for the GLM? What's the formula? Okay. I tell you that. Of course, it's ln y x beta x square I n, and we've computed that earlier, and we talked about this also this week. So it was this formula n half times log 2 pi minus the whole thing minus n half log sigma square minus 1 over 2 6 square. I put them below each other. Times y minus x beta transpose times y minus x beta. Yeah, so that's the log likelihood function, as we've learned in statistical methods. So we now basically need to write this up here. So yeah, we can extract input, and it's easier to see. So we just get our data out of the structure. So we're extracting the input, and now we need to evaluate. This is always a little bit tricky. How do I do this? Oh, it doesn't really matter. So I'm calling this N. Maybe I pass in. Should I? I mean, there are two ways. Well, I put it in. It doesn't hurt. So I also pass in n directly, then I don't have to use size again. Scalar number of data points. P. Do I need this actually? I don't think I need it, so we don't need to put it in. So let's pass in the number of data points as well, which we have evaluated up, which we have defined actually up here. So let's also extract that again. And then now evaluate this. So we need n divided by 2. Actually the minus this, minus times log 2 times pi. We need to subtract from this n divided by 2 times log 6 square, and we need to subtract from this the most important thing, which is of course y minus x times beta transpose y minus x beta. It's getting a little bit long. Just move the space there. So let's see whether that works. Oh, there's already a mistake. So this is just in MATLAB format, the formula that you're familiar with from statistical methods. And let's see whether everything works. And so far not. Okay, that's a typical error. So what is, let's first look at the dimensions. Y x times beta. Okay, there's something wrong with so with what I'm putting in here. So the word beta was a row vector, and of course it needs to be a column vector. And then we get the log likelihood, which is minus 203,163. Single value. Yeah. So now we have for this data set that we sampled here, and this setting of the beta parameter, assuming that we know the true but unknown sigma square. Actually, this should rather be called sigma true but unknown. I also have to change here. I'll wait here. That can be like this, but here we need to specify this. Oh, that's a little bit cleaner. Now for a different sample, of course we get a different log likelihood value, although the parameters are the same, but the data is now different, so we get a different value. Now, what is actually quite instructive is to visualize this. So let me show you that. How are we doing with the time? Well, take like 15 or 20 minutes. So let me show you there we can actually use some for loops. So let's assume that we so call it different. So let's say that we want to vary our beta 1 parameter, so the offset between, what is the true but unknown value? It's 2, so let's do that between 0 and 4. So I'm creating a space here between 0 and 4 with 100 data points for beta 2. Let's say min space 0 to 1. 1, E2, and now let's look at our likelihood surface. So log likelihood surface we initialize as none. So initialize to none. Now we're using a nested for loop to fill in this, like we've seen this morning. So for E to res and for J1 to res. And this is iterate over beta parameters. we are now evaluating the log likelihood, which we still have to actually return here. So let's do like this, and let's return like this. Because that's very instructive and something that you should always do when you estimate models. It's now not the most efficient code because I'm specifying the input, specify log likelihood input again and again, which one doesn't need to do. The important thing is that we pass in beta as the combination of the beta 1 value for I and the beta 2 value for j. And then we can specify log evaluate beta setting and collect log likelihood values. So this is now our log likelihood surface at location ij, and there we put in what we get from our log likelihood function, so this, and then it's overwritten. And then the great thing is that we can look at it. And maybe we look at it next to this one. So there is in MATLAB a function called ImageSC, which allows you to visualize 2D matrices. So we now have a 2D matrix or array log likelihood surface, and one needs to pay a little bit of attention of how this is oriented. I always get that wrong, but let's first have a look. This beta, I think it must be in this order, but we will see that in a second. So let's run this. After a little bit of debugging. Let's move this and maybe decrease the resolution a little bit. So now we are seeing the log likelihood function for this data. So you see that the data is actually quite noisy. So I think it's much more intuitive if we go to less noisy data. It's essentially the same. So here we have now the beta parameter, the one beta parameter and the other beta parameter, and you see, if you think about that, the color code represents the height of the function, that the maximum is approximately here, which is of course the value for the true but unknown parameter. Now with fmin search we can basically walk through this space numerically and maximize it. And this is the last thing that I now want to show you, but very instructive thing is to always look at these likelihood surfaces. So let's do the estimation now. So essentially fmin search, that's the analytical, and here we do the numerical. So we obtain our beta head numerical, and we can also have our I think that's all we want. So we use fmin search, and now one has to pay a little bit of attention. So one way to do that, actually I have to change my log likelihood function a little bit. If I want to use fmin search, I need to put in beta directly. So I need to change the code a little bit. These are the additional arguments that the log likelihood function needs. And this is the parameter argument. Oops, of course that, yeah. And then we, and of course we need to adapt that in our function here. So this is just because we want to use fmin search for a specific argument of our likelihood function, namely the beta parameter. And then we don't need this. So, and that should do it. Let's check whether things working. Yeah, so that still works fine. And now function handles and fmin search. So this is why I started the whole thing. We want to apply fmin search now to our log likelihood function, and specifically to our negative log likelihood function, because we want to do maximum likelihood estimation and not minimum likelihood estimation. But now we need to tell MATLAB in some way that we want to put in a function. So we need to specify a function handle, and there are different ways to do that, which is a little bit annoying because you can you never know what is the best way, and MATLAB changed that a little bit over time, but I'm showing you the latest version hopefully now. So if we look into fmin search, we can either I don't think so. This I think this is actually what I want here. Yeah, so we are putting in this thing here. So let's have a look what this does. Well, actually, why am I confused? I need to check something. Okay. Function handle, that's the input arguments. This is the anonymous function, but yeah, so the thing is that this, I think, does it automatically. Okay, so the function handle can be specified as this. So this should be now the handle for the SLR log likelihood function. I think you can do it with this add. That's to work. Yeah. So this basically now holds a pointer to the function that we want to use in fmin search. And I think in principle one can actually pass that to fmin search. But one can also create actually the function handle on the fly, and this is actually then easier to see. So we're doing that. So we are specifying, like I did in the script, we are using add beta SSLH beta LLH. So let's have a look on what this is doing actually. So now this way we specified a function handle again, so a pointer to our function. But what we also need to tell MATLAB is if it uses fmin search, this function has multiple input arguments with respect to which argument it should actually apply the fmin search. And this is defined by this add beta. So what this says is to fmin search, minimize this function here as a function of beta, and given this definition of LLH, this of LLH. And this we still, although we did it up here, need to specify here. So for the numerical estimation, we first specify the additional argument, which of course, and this is important, takes our data in. And then we apply fmin search using a function handle. The function handle is this bit here. Yeah. So if you, like I showed you before, there it is. If you use this syntax, MATLAB creates a pointer to this function and also incorporates that it should be a function only of this input argument. And that's essentially everything. What one can also specify is a starting point. So this is a numerical approach. So you might want to give it a starting point, beta 0. And let's say for specify initial value for beta 0. We use 0, 0, and I think this should now run. Not quite. Beta LLH, beta LLH. So this is of course real life, so you get sometimes bugs, and now we need to check what's going on there. So can we actually get in? Yeah. So that looks fine. And yeah. What fmin search doesn't like is the fact right now. So I like my way of putting in structures and getting out structures, but MATLAB for fmin search doesn't like that. So we have to, as output here, specify just the log likelihood scalar. So it needs to be, if fmin search is applied, it needs to have just a double scalar output, which means we have to a little bit adapt this code here, but that also doesn't hurt much. Then we can directly get that out. So, and now if we run that, still light. And we need to specify this, of course, as L. So, and yeah, so now actually fmin search was applied. Of course, it was pretty fast. And it came out with very nonsensical values, as you can see here. Beta hat n beta hat n came out as these values. So something was wrong. So why was something wrong? Is anyone still with me? So why did this not work? No idea. Okay, so what the function that we wrote here evaluates the log likelihood, and we want to maximize the log likelihood, but we're applying a function that minimizes something here. So what we actually need to do is consider the negative of our log likelihood function, yeah, because if you minimize a function, minimizing a function is the same thing as maximizing its negative one, or in this case, maximizing the log likelihood function is the same thing as minimizing its negative. So we can put either the negative value here. We could also, of course, put the L as negative. That depends a little bit on your taste. And now if we run this and look at our beta, what's it called? Beta hat n, then we get something much more meaningful. Beta hat r, and you see that actually our numerical and our our analytical are virtually identical. So let's finally visualize that, and then we are done. Of course, I decide when we are done. Let's see, make the font size nicer, make some lyrics labeling. Is that correct? And this is always tricky with MATLAB. I want to show you that in the end because that's really what you want to do every day. Jesus, that was not good. But there's no other way. the problem occurred earlier. So again, this is our log likelihood surface, and did I do that correctly in terms of the beta 1 and beta 2? So beta 2 was 0.5, yeah, seems reasonable. And now in this space of parameters, I want to include our numerical estimate. So we plot beta hat n, and then one always has to think this way around, I guess. Let's see what happens. So why does it do that right now? I don't know. Just trying to make the figure nicer so it's easier to see. So, so this is now where it got its, that's the numerical estimate. And of course we can also plot our true but unknown value. So that would be beta TBU, beta TBU. Let's do that like this. Does that make sense? It doesn't make sense. So, and you can see that they are essentially at the same location. So, but you can also see that here because it fits very well. So the last thing, I increase the noise again, and then we might have some deviation, as you see here. So the true but unknown beta parameter value is this black dot, but as you can see, the likelihood function is a little bit shifted. And its maximum is actually here, so our parameter estimates deviate from the true but unknown estimates. Yeah. So now I think I tortured you enough, but this is really, yeah, this is why one does the whole thing of MATLAB programming. Yeah. So this, one doesn't do programming just because one is nerdy and wants to sit in a basement doing programming, but because in science one wants to exactly do this kind of thing, namely specifying theories, quantitative theories, which we are doing here in terms of a GLM, and estimate its parameters. And if you want to become a scientist, you should empower yourself to come up with quantitative theories and estimate its parameters and then do model comparisons. And you can only get there by working through these kind of examples. So I stop here. I had a lot of fun in the last hour. I don't know about you. But yeah, it put things nicely together. So yeah, let's